Right, okay, I think we should make a start. Today I'm very pleased that we have Gavin White here. Gavin is currently Director of Structure Group in Cambridge office of Ramboll, and he has done many timber projects over the years. And okay, so I think that's it. I'll just hand this over to Gavin.
No problem, no problem. Can you all hear me? Okay, yeah. So my name's Gavin White. As Wen-Shao said, I'm a Director of Structural Engineering at Ramboll in Cambridge. I've been with the firm for about 15 years now. So I started off, it was a company called Whitby Bird, and now we're now a company called Ramboll. So just a little bit about Ramboll for those of you that don't know us. We're about 13,000 employees in total, founded in Denmark in 1945, and at the moment we employ about 1,000 people in the UK. In the structures teams, we're probably about 250 in the UK, and we do, we're a multidisciplinary consultancy, so we do structures, we do services, we do acoustics, we do lots of different things. Yeah, we design about more than 10 million metres squared of buildings every year, so quite a lot. We have offices all around the world and in the UK. I'm based in the Cambridge office, just up here. We do have an office in Bristol. Our head office is in London. Probably got about 400 people in London, but there's about 25 of us in Cambridge. And I lead the structural engineering team there. And I've been in the Cambridge office for about 10 years now. In that time, I've probably worked on about 45 different cross-laminated timber and timber buildings. So what I'm going to talk about today is just some of my experiences, advantages, issues that we've had when designing with, and just things to watch out for. So these are just some of the projects that I've worked on, and over the last 10 years, we've done. We looked at a car park in timber. That didn't get built, unsurprisingly, but we've looked at some schools, done some schools. We've done an education facility for the University of Cambridge. We've done some residential properties. We've done some other teaching blocks, so lots of different things. And historically, the timber has come from an educational background, so lots of schools and that kind of stuff. That's where it really started about 10 years ago. And around the last 3 to 4 years, it's moved quite heavily into the residential sector because people are seeing advantages of building with it in the residential sector. So who knows what cross-laminated timber is? Who's ever seen a piece of cross-laminated timber? Anyone? Few half hands going up. Okay, that's fine. I'll explain a bit more about it. It's just interesting to understand what it is. And who's thought about designing with it before? Or who is doing their projects with it or thinking about it? A few people? No, that's good. So I would encourage you all to be looking at it because I think it's got a lot of advantages when used in the right situation. I think there are some situations where you can force it in there and it doesn't really work, but most of the time it can work. So cross-laminated timber is layers of softwood laid on top of each other orthogonally with glue in between and put in a big press and press together. So they make big panels. So they come in panels around 13.5 metres long by about 2.95 metres wide. They can manufacture up to about 18 metres long, but to transport to the UK, you can only have about 13.5 metres long. 2.95 is the maximum width, well, I say maximum width transported to the UK. You can have up to about 3.5 metres, but the more standard width is about 2.4 metres. And this is quite important in terms of the sizes, because the cross-lamination means that we are, within a panel itself, it's two-way spanning, but when you start to put the panels together, you're really only one-way spanning, because you can't have a moment connection between the panels. Well, you can, but it's very hard and very expensive, and you shouldn't really do it, to be honest, unless you really, really have to. And we've only ever done it, I think we've only ever done it once on all those projects. So it's something that really we should try and avoid. So it comes in thicknesses between about 50 millimetres and 300 millimetres thick. So interesting for you who are doing your scheming, design and your projects. Walls will normally be between about 100 mil thick up to about 140 mil thick, and floors will be anything between about 140 to about 200, 220 thick, something like that. If you're starting to look at your floors and they're coming out about 300 thick, you've got the wrong solution, in my opinion. This should only be used in a very occasional situation in terms of the 300mm thick for a floor, because it's not, whilst timber is good, we need to think about how much we're actually using of the timber, and we're not using this efficiently. We're only really using the bit at the top and the bit at the bottom, and the rest in the middle is just a spacer. So it's not an efficient use of the timber. So where does this timber come from? Well, it comes mainly from Europe. We don't have any manufacturers in the UK who produce timber, or produce the CLT. About 90% of it comes from Europe, so from Austria and Germany, and the rest comes from, well, we don't really get it from here, but it supplies the market in the US and down in Australasia. So three main manufacturers, suppliers to the UK are KLH, Bindholz and Stora Enso. They're the three main ones who supply CLT to the UK, and they do it through their kind of the subcontractors they have. So KLH do it through KLH UK, Bindholz do it through B&K Structures, and Stora Enso do it through a company called Urban or G-Frame. So there's different ways to get it to the UK. So we'll turn up on the back of a lorry, much like this, with panels stacked up. Now, if you remember that 2.95 and the 2.4 I mentioned, a typical back of a lorry is 2.4 metres wide, just about. So these are 2.4 metre wide panels. If you start going for the 2.95 ones, you have to stack them vertically. And once you stack them vertically, you're not doing it very efficiently, and you're transporting a lot of air. You can't get as much volume on a back of a lorry. So 2.4 is much better for a general use. So they come on the back of a lorry much like this, and ideally they're placed in reverse order. So this one up here is the next one you need, next one down is the next one you need. So you lift it straight off the back of the lorry and into position on site. So it can be very quick and easy on site. That doesn't always happen. Sometimes there's not enough room to have a lorry sit there for 2 or 3 days while they unload it. So you may have to unload it and then take it off again, which you can do. So when it's lifted off the lorry, it's lifted into place with straps, much like this, a couple of lifting points, and lifted into place. So this is a residential project that we worked on, one of the first ones we did in Cambridge. A small house, I say it's a small house, about £1 million house at the time, about 10 years ago, so it's probably worth about 3 million now. But this is how they lift them into place, typically from mobile cranes on smaller projects, and just put it straight into place and then fix it with your angle brackets. So what you might be interested in, and also when you go into consulting engineering or whatever it is, if you're looking at the structural side, is applying it within your work. Well, one of the things that I've certainly seen, since 2010, is the volume of CLT used in the UK has gone up dramatically. I haven't quite got the numbers for 2015 yet, but I've got I've seen some indications, and it's carrying on for 2016 as well on that trend. So lots of people are using it, and the volume of CLT used in the UK is going up. Equally, people are getting more interested in it. You know, they've mentioned it in the press. I'm sure if you have been looking at it, you'll have Googled it, and there's loads and loads of articles about it in the press. So, and that's been increasing as well over the last few years in terms of use, in terms of people being interested in it and wanting to learn more about it, which I think is great. It means that we can start to use more of it and start to use it in the right kind of ways. So over the last sort of 10 years in the UK, about 1 million metres squared of internal area of buildings has been completed. So, which is massive. I mean, a typical secondary school might be about 10,000 metres squared. So lots and lots of buildings have been completed in it. So if people try and say it's new, it hasn't been used before, it has been used before quite a lot in the UK. So it's not as new as quite a lot of people think. So question is why when you've been looking at it, or why when you've been thinking about it, is there anything that's stopping you from using it or thinking about it? I mean, it may be that you haven't really looked at it, but are there anyone got any thoughts about why wouldn't people use it? Anything? No? Okay, well, I'll carry on. These are some of the reasons why we found that people don't use it, why architects, clients, developers don't like to use it. So cost, that's a big one. Then there's things like there's not enough trees, it catches on fire, there's not enough supply chain, people don't know how to design with it. Well, hopefully that will change if more people like Wen-Shao teach people how to design with timber. I mean, one of my bugbears is that we don't really teach timber in engineering kind of degrees. There's a lot of concrete, there's a lot of steel, but not enough timber. So hopefully, coming here, you'll actually get some timber knowledge, whereas most universities don't. So I think, hopefully we can get around that one. But, there's lots of different things there that stop people from using it. So I think what I'll go on to now is just some of the advantages that I've seen and the Ramboll have seen as to why you should consider it on projects. So this one here, CLT it's very fast to erect it. It's very quick to put up. So typically a CLT building might go up about 15% quicker than an equivalent steel or concrete frame. So that 15% means that you can be on site for 50% less time, and you don't have to pay your site staff and everything else, and you don't have the contractors' overheads and prelims, so all their welfare and all their site cabins and setup. You don't have to pay for that for those 15% of the time. So it means you're starting to bring the cost down because of that. Also, when you're looking at doing we did a 10,000 metre squared school. The CLT alone went up in 16 weeks. To do equivalent steel or concrete frame would have taken about 32 weeks, so twice as long to do the frame. Obviously, once you've taken into account the rest of the programme, it comes back down to the 15% I mentioned earlier. But it's about 50% quicker just for the frame erection, which can be quite important. So when I talked about costs earlier, the costs are quite key to this. So a concrete frame might be about £200 a square metre to build it. A CLT frame will be around 250, so £250 a square metre. So it's already 25% more expensive, which is going to be a struggle for any client and everything to pay that extra money. Well, you've then got to look at, that's just a pure frame cost. When you start thinking about the saving on the programme, then you can really make that saving and you can really bring it down. And I had a conversation with a cost consultant just a couple of days ago on a project that he's looking at, and it's a £110 million project, and he was looking at it in concrete, it was 110 million, and he looked at it in timber, so cross-laminated timber, and he got it down to £100 million. So he made a 10% saving just by going with the timber, despite the fact that the timber is, as a frame cost, more expensive. So costs are coming down. Brexit hasn't helped because we buy it all from Europe, so we have to pay for it with the exchange rate in the euros. So that really hasn't helped, but it's still, this cost plan was only done last week, so it really does show that you can get it down and the cost can be competitive. Another thing that we found is that the construction waste is very minimal on site. It's all prefabricated off-site, it's all cut to 1-2 millimetre accuracy, so the waste when you go to a site is actually quite small. The same school I mentioned earlier, the 10,000 metre square school, that had 2 skips of construction waste during the whole superstructure erection. So that's really, compared to a normal construction, that's very, very little waste. Equally, there was only 2 cranes and 8 people on site during the whole superstructure erection. So that meant that health and safety wise, there was less people on site, less risk of accidents. So from a designer's perspective, that's good because we're already trying to reduce the amount of people and the risk of accidents on site. Air tightness, the CLT, because it's cross-laminated and it's glued together, the air tightness of the panel itself is very good. It doesn't really let air pass through it. When you join them together as well, you half-lap them, you screw them together, and you create a very good air tightness, a seal there. So what you actually find is that CLT buildings are actually very airtight. So instead of having an air leakage rate of, well, the building regs say we need to be down at 5 metres cubed per metre squared per hour, typically a CLT building might be down at 2.5, 3. So that air leakage rate means that you don't need to put as much heat into the building, so your M&E kit can be smaller, and therefore you make savings on that. So there's lots of added advantages to it that aren't immediately obvious from just looking at the CLT. The CLT, if you look at it pure mass by mass against concrete, CLT might be 500 kilograms per metre cubed. Concrete will be 2,500 kilograms per metre cubed. So there's a big difference in weight. When you look at it in terms of obviously how much structure you need to put in, how much building weight you need to have in there, and all the people, a CLT building will be about 30% lighter than an equivalent steel or concrete frame. So that's when you take into account all the floor finishes, all the desks, all the people and everything in a building. So that's quite a big saving. So that means that if you've got underground infrastructure such as tunnels, sewers, or weight restrictions on the building, that can make a big difference. That means you can go taller, you can do bigger, you can do different things. Equally, if you don't have a restriction and you're just going into the ground, you might even be able to make a 5-10% saving in the ground in terms of cost, in terms of program. Again, that adds to the benefit of building in CLT. And because your CLT forms your walls, your external walls, you can actually avoid a lot of secondary steelwork. So you're just fixing your cladding straight to your timber. So you don't need to think about putting in extra bits of steelwork just to support the cladding. So a very little bit on the engineering, because I'm going to teach you about how to design with CLT. Leave that to Wen-Shao. I'm just going to talk a little bit about the very basic principles, which I think, for me, I come back to day after day in terms of engineering. So it's really important with something like timber to understand what the material properties are, and going back to first principles. So for me, thinking about timber as a bunch of straws is a very good way to think about it, because when you think about a bunch of straws, you can squash them quite readily in one direction, again, across the grain. But if you try and push on the end of a bunch of straws, it's actually very hard to squash them, and that's really important. The cross lamination takes part of account of that, but this is really important for thinking about moisture movement and crushing of timber and connections as well, because you don't want to be screwing into the end of a bunch of straws, you want to be screwing to the side of it. So it's really important to understand that. And just so you don't take my word for it, this is a microscope image of some wood. You can really see the voids in here and how it would really work as that kind of straw-like nature. And we'll come back to why that's important later. So a little bit about the engineering. By cross-laminating it, we're trying to stop these layers from sliding over each other. So we're trying to stop that from happening. But what you do get is you've got all your straws in there. So what you end up getting with is rolling shear. So all those straws roll over each other. And this is just one of the failure mechanisms we're trying to avoid, is a rolling shear failure, which is actually one of the most common ones in CLT in terms of how to work it. So you've got your top and your bottom chord, which are doing the work, as it were, and this is the spacer layer, but then it's also rolling over each other. So those straws are rolling over each other, and you get a rolling shear failure. This might even be one of your pictures, to be honest. I'm not sure. So obviously what we're trying to do is take all our gravity loads and put them down through the floors, so and to the columns and down into the foundations. Very, very simple stuff. When we start to go tall as well, we need to start thinking about how we can make the building stiff enough so that it doesn't move too much in the wind. So we've got different bits of stiffnesses. We've got connection stiffness. So when we connect the panels together, they try and rotate as the wind blows, and they're only held together with screws and nails, and they'll slip slightly. So you get a bit of rotation at the top. You've got normal bending stiffness. You've got shear stiffness, so the panels sliding over each other as the wind blows. And if you've got a podium or a ground floor slab, that ground floor slab is going to deflect slightly. And if you think about the lever arm on here, just a small movement down here can have quite a big movement at the top. So it's quite important to understand all of these things when you're starting to think about designing with CLT. No talk on timber would be right without talking about fire. It is timber, it does burn, and you need to think about it. This is a project in Nottingham. This was it before it burnt down, and this is the images after it burnt down. It burnt down during construction. They hadn't got the fire compartmentation in there at the time, and I mean, it's one of the risks of burning with timber, especially during construction, is any kind of electrical fault or anything that causes a fire. And if it's not protected properly, or there's not the right kind of fire alarms, you can have this kind of thing happen. One of the positives that came out of this, there can be a positive out of this. It burnt down on a weekend, so no one was in there, which was definitely a positive. But it was designed for a 2-hour fire rating. It stood up for 6 hours before it fell down. So immediately, you could say we're possibly over-designing then, because this was one of our projects, but it was, because it lasted for 6 hours and it was only meant to last for 2. But it shows that the codes are inherently conservative. with what we do. So, which, you know, when you're a consulting engineer, there's a tendency to, you know, design things to 80% capacity or something. To be honest, you could design everything to 100% capacity and it will still be fine. Probably design it to about 120 and it wouldn't be a problem at all. But so it's just interesting to understand the fire nature of it. There are different ways of doing the fire design. One of them is to leave it exposed and have a charring layer. Timber chars at about 0.7 millimeters a minute, typically. So after a certain amount of fire, we know we've got some timber left there that can take the load. As long as that timber is man enough to take the load, it's fine, it can work. Or we can cover it with some plasterboard. That gives us a bit of fire protection, and then the rest of it is taken in the timber and charring again. So we like doing experiments, so we built ourselves a barbecue out of CLT, which on a nice sunny Saturday afternoon, yeah, I'm sure you get sunny days here at some point, but it wasn't very sunny today. And we had some nice burgers, and we put the coals on there. When we put them on, that bit at the back, it went up in flames for a little bit, and then it came back down, and it just smouldered. And after an hour, we took the coals off, and we just wanted to see what happened. Did it carry on burning? Did it carry on charring? Did it smoulder? What happened? Well, it carried on smouldering for about an hour, and then it kind of just stopped. And that was it. It didn't suddenly keep on burning, didn't suddenly disintegrate. Probably only use it about 5 or 6 times, and then it would probably would disintegrate. But for us, as engineers, it was quite nice as a little, you know, a very non-technical experiment on how timber performs under fire. So, and it reassured us that what we were looking at in terms of the code and how we were designing with it was kind of right. We kind of understood it a bit better because of this. Vibration, I know I've been talking to Wen-Shao about this earlier. When the codes at the moment say design it for 8 Hertz natural frequency for a residential floor, that's not entirely the best way to look at it, but, you know, and then there's no real guidance for schools, so we go down to about 6 Hertz, but it's a rule of thumb that we worked with over a number of years. But vibration is quite important. It is a lighter weight than concrete and steel, therefore you do need to think about it more in terms of the vibration criteria. Movement, so coming back to that bunch of straws we were talking about. So in a floor, so this is a section, so this is a wall up here, this is a wall down here, this is a floor going in. These are all there's no end grain here, this is all cross grain, so these are all the bunch of straws. So when there's a load coming down here from the wall above, it's basically going to squash those straws, it's going to squash them down. You're also going to get drying shrinkage as the timber dries out. And what happened on this project is, this is a rendered facade, and basically the floor is squashed down and basically popped the render out. So it's broken the render and it's popped out, and that's the line you can see along here. So movement is really important to understand in timber. You've got to think about it early and think about how you mitigate it. On this one, the simple thing to do would be put a movement joint in the render. It's very simple to do, but it wasn't done, and therefore it cost a load of money for the contractor to come back in and fix it. So movement is very important. You can try and avoid this by doing things like this, where you take the end grain straight down and you put it onto the end grain of the wall below. So this is the floor coming through here, here, and here. So you can do that, and you try and put the end grain to the end grain, so you're not squashing any straws. You're only going on the end of the straws. This creates problems in as much as then you have a lot of wastage of your timber, because you're cutting out this section of the wall there, there, and there, and you're cutting out this section of the floor here and here. And when you design with timber, when people build with timber, you pay a lot for the timber itself, for the volume of timber, and you pay for it as a big 18 meter long by 2.95 meter wide panel, and anything they cut out from it, you still pay for that. So you want to try and avoid these kind of things. So we've been working on a 10-story building, and what we've actually done on this one, we've actually cut out little sections of the floor, and we put a grout pocket in there. So we put a pocket of high strength grout, and to try and stop our crushing and stop the movement of the timber frame. Because we looked at it and we worked out that if we didn't do anything, we'd end up with 60 odd mil of movement at the top of the building over the lifetime of the building, because it would settle down, it would shrink down, and it would crush under the weight of it. So obviously that's not good for a number of reasons, for your lifts, for your thresholds, for your finishes, lots of reasons for your cladding and everything else. So we knew that wasn't going to be acceptable to the client, so we looked at various options of stiffening the floor. We came up with the, in conjunction with a subcontractor, the grout pocket, and we got the deflections down to about 10 mil. So, which is not too dissimilar to a concrete frame or steel frame, which will have some axial shortening in it anyway. So the client was very happy with that. He was used to concrete frame, so he was pretty happy with that. So a little bit about scheming, which may well be helpful to you. If you can try and keep that and avoid this. This means you'll have transfers, you'll have a thicker floor slab, it'll cost more. You can try and line up your load-bearing elements, you'll have a much more efficient structure, and therefore you're much more likely to make the CLT work, or to be honest, have a more efficient structure, whatever your structural form. So, yeah, it's a more complicated design as well. You know, if you're short on time, which we often are as engineers, trying to make the design as simple as possible is better for us, while still having the architectural freedom to do something different. So you've got different types of panels. You've got ones where the outer grain is going vertically, so through here, or you've got the floor ones where it's going horizontally. So this is the floor, they're here. Whereas if the outer grain, so if those lines were going in this direction here, that's what we call a wall panel. So it's just different ways of the outer grain and the orientation depending on what you want to do with it. So typically offices can span up to about 7 meters, residential up to about 5 meters. So they're just rules of thumb, but they're fairly standard. You can go more, you just might end up with a thicker floor and something that's not necessarily as economical. Because it's a lightweight material, if you can try and keep your finishes lightweight as well, that helps because it just means it's a lighter building and you make efficiencies with it. So if you can have things like timber boards, stud partitions for your timber boards for your floor, cladding, something lightweight, zinc, panelization, panels, that kind of thing, and try and avoid bricks, thick screed, block partitions, that kind of thing. Just makes it easier. You can have exposed timber and it can look very nice. This is a staircase that is actually made out of one panel, and even the balustrade is recessed into it. So it does cost more to have it exposed because they have to do more finishes to it to make it a nice finish so you can walk past it and you can touch it. Also, just coming back to the fire, if you have it exposed, you have to put more timber in there because you have to account for the fire case. So you have to put more timber to make it thicker so that when it burns away, you've still got enough timber left. And connections can be a bit more tricky because they have to be hidden away. You don't want to see lots of bolts. Well, you might want to, but typically you don't want to see lots of bolts, screws, angle brackets, that kind of thing. And one of the things to try and do is try and get your coordination with your mechanical and electrical services done early. Try and do that so you can pre-cut all your holes in the factory for all the services. You can even prefabricate a lot of your services and put those in as well. So there's a lot of coordination things that can be done nice and early and try and avoid things like this, which is an afterthought of a hole in the timber. So just a little bit about the details. You know, as consulting engineers, most of the time, most other companies will design maybe a scheme design in timber and then it will go to a subcontractor. About 10 years ago when we started looking at this, we took the decision that we're consulting engineers, we should be able to design in steel, in concrete and in timber. There's no reason why we shouldn't. You know, it's a material, we just have to learn how to do it. So we decided that we would do the design for that. What you'll find is when you do a lot of timber design, connections do govern quite a lot of the member sizes. Certainly with beams and things, you can design a nice glulam beam, but you can't get the forces out at the end of it, and you have to start making a glulam bigger. So at first we didn't do the connection design, and then we went, hold on a minute, we need to be able to do the connection design as well. So now we do the connection design and the timber design, which most consulting engineers won't do. But I think for me, I didn't really see the point in being a consulting engineer if I couldn't design with most materials. So these are just different connections. You've got this is a parapet here with a floor here and a block. This is sometimes we put steel in there. You can put steel together with timber very well. You'll see here these interesting. These are little holes, so you can actually put the drill through and screw that in. Because you've got to think about buildability. How are they going to screw that in if you can't get your drill bit in there to screw it? So you've got to think about these kind of things. So it's quite quite an interesting way of thinking and a much more practical way of thinking than potentially just designing a steel beam or a concrete beam. So typically it's jumbo screws, angle brackets, nail plates, that kind of thing. So this is on our 10-story building. We've got our staircase and our lift shaft also completed out CLT, and these are just nail plates. And this guy's got a rather thankless task of going around and pretty much filling in all of those holes with nails. So it's fairly simple technology, just used in a different way. When you start to go tall, you start to have to think about how you're going to transfer those forces between the panels. So if we think about when you start to try and push the building over, you're going to have overturning forces. So we developed up this kind of detail, which this is a bolt through the floor. So when our building starts to topple over, you can imagine you get uplift on one side and a crushing force on the other. So, and the wind can obviously blow from two directions, so you have to have uplift on this side and crushing on the other. And these ones in the middle, they take the shear. So it's basically a third in uplift, a third in shear, and a third in downforce. So that's just typically how we look at it in terms of the engineering design. And one of the things that really interested me and why I got into the timber and sort of design in the first place is, I've been discussing Wen-Shao. We're not even sure that that's completely right. We think it's right, but we don't really know because there hasn't been enough research done into timber and how it reacts. So, we're pretty confident, but I'm sure if we did this again, even now, we probably did this design 2 years ago, even now we'd probably do it slightly differently. We try and be more efficient. We're pretty conservative with the design at the moment, and we want to be more efficient, and then we'll make it cheaper, easier for people to build with it, and then we'll build more with it, and it'll be more sustainable, and it'll be greater, and it'll be really good. So that's what partly got me into the timber side of things, is that I can still, as a consulting engineer, I can still do bits of research. I can still, push the industry forward and have a bit of fun with it as well. So this is the detail we came up with on this one. You can recess it into the wall. It's a single shear bracket on this one, but you can play around with it and try and make it work more efficiently for the finishes. The reason this is recessed in is because we've got finishes on there, and we don't want to make the corridor narrower or the building wider just for a single angle bracket. We've also got balconies on our project. These are our steel bolt-on balconies. If you have inset balconies, so balconies that are recessed into the building, I think you could do those in CLT, but anything sticking out from the building, I think the weather protection of that is just too risky to have it in CLT. It's not meant to be something that's left exposed externally, certainly not with direct wetting. So I think the risk is too high. But these have got little steel brackets, and this little blue line here is a thermal break to take it through to the outside. So a little bit about construction. It's about a 12-week manufacture period, and then they have about 2 to 3 deliveries a week. And what you can generally do is you can start erecting on the ground floor, and then once you're 2 floors up, you can actually start fitting it out underneath that. So you can really start overlapping your program into making those program savings. So I've just got about 3 case studies to go through now. First one is Dalston Lane. So this is our 10-story. It's got 9 stories of CLT, 1 story of concrete. So that's a concrete podium down here, which has got retail space in it. So it's got a different grid, different structural grid. So it made sense to do it in something different. Concrete was a good option here. And it's got about a 400 to 500 thick concrete transfer slab, and then the timber goes straight off the top of that. So one of the main reasons why we chose CLT on this one was we've got cross rail and high speed rail link, one underneath the building and one right next to the building. So we had restrictions, we had a weight restriction on the building. And when we looked at it in timber, we could do this big. When we looked at it in concrete, we can only do 15 fewer flats than we did in concrete. So immediately the client, by doing it in timber, he's able to get 15 extra flats. And we actually designed it so that in the future, he could put 20 extra flats on top of the building. So, from his point of view, he's got 15 extra flats, which might be 7 million extra pounds in income. He can actually have an extra 20 if he got planning permission for them. So for him, it was a fairly obvious choice why he went for this. So this is to do with this 30% lighter kind of aspect. So what we did on this one was we were working for the client at the start. So we were here in the design team. Then when it went out to tender, we actually got novated across to the CLT subcontractor. So we worked for the supplier at that point, which is fine. We worked with this particular supplier quite a lot. So it was quite an interesting way of doing it, working for a subcontractor, but it was a good way. And we learned a lot from them, and I think they did from us as well. One of the key things about when you're going tall with timber is to think about the fire regulations. So when you go above 30 metres, you're into about 120 minutes fire rated situation for your structure. When you put on plasterboard on the edge of a timber, you can only get about 49 minutes maximum fire protection on there. So that extra time needs to be taken in the timber. So if you're having to take, that extra time in the timber, you're having to make the timber very thick. So if you're above about 30 metres, timber starts to become challenging to make the economics work. On Dalston Lane, we're at 29.97 metres to the last habitable floor. So we're just inside the 90-minute range, which means we can be quite cost effective. Because as soon as you go over that, the whole building has to be 120 minutes, not just the bit that's above it, but the whole building. So it can be quite a challenge. There was originally a roof terrace on the top, which meant that you could access it, and that was above the 30 metres, but we quickly got that changed, so there isn't one up there, so that we didn't have to design for the thing, because it would have added about 15% to the timber volume of the building. So this is a picture of it, probably about this time last year when it was going up, and you can see here, these little strips here in between the windows, they're actually there as temporary edge protection, but they're also there to stop it, and they lift it up to stop the back breaking in terms of lifting the panel, because this from here all the way across to there, that's one panel, lifted in one go. So it's very quick to erect this. Mayfield School is a school we completed a couple of years ago in London, all built out of CLT. The key thing on this one was the BIM process and the design process we went through. So we had our structural model, we had an MEP model done in 3D as well, and we had the architectural model in 3D. So over a period of months, we coordinated these and made sure that the CLT had all the holes in the right place. Then what we did is we just gave our model to the CLT fabricator. He took that model and he started to look at the panelization, so where he's going to split the panels, and look at how he could fit them onto his mother panel. So this might be the 18 metre by 2.95 panel, and he looked at how he could split it onto there and panelize it up. And for him, he's trying to minimise the wastage, because if he can minimise wastage, he can have a cheaper price and he can win the contract. But for us, it meant that he just gave his model back to us. And we took the model, we overlaid it with ours, we did a clash detection on it, and we spotted things that weren't going to work and spotted things that were fine, and then we sent our comments back on the model. So it was all a very seamless process. There's no, when we get through steel drawings or that kind of stuff, we have to go through, we have to check each one of them, and we check them by hand on paper. Whereas this, we were able to do it much more in a 3D in a collaborative environment. And this is a staircase in that school, and typically we don't use the CLT, leave it exposed to walk on. It's a softwood, it will get damaged, it will scuff and everything. But here it's not a general walking space, it's occasional use, and actually can make quite a nice space in that kind of situation. And the last case study is University of East Anglia, Blackdale. So this is student residences. So this is 500 student rooms and a central block of ancillary laundry space and cafe area. So we started working on this in, it was about September 2014. Within about 22 months, it was built and occupied, and people were in there living in it. So they only had 62 weeks on site to build the 500 student rooms. I don't know how long your one here took, but probably
Several years.
Probably a bit longer than that. So it can be very quick, and this is it during construction. And you can see here they're building up here, they've already got the windows in here, and they'll be putting the first fix for the M&E services in. So they can really overlap that time, that program on there. And here you've got bathroom pods, which are lifted into place. So they're lifted in. They're not lifted into the exact location, they're lifted in on skids and then moved around once the rest of it is built, so they can get the building up, get it watertight and start fitting it out. And you can see here, there's quite a lot of lay down area for the panels, but that was just to make sure that they didn't get caught up with any delays with panels coming across from Europe and things. They needed to keep the program going as fast as possible. So, a bit about research and development. One of the things I'm quite interested in is how tall we can go with timber, and how tall we can go with pure timber rather than having a concrete core or something to help us go tall. So Dawson Lane, that's to the top of the building, the 33.8. It's not the habitable floor. So it is currently at the moment the tallest pure CLT building in the world. There are the tree departments in Norway, which is a glulam hybrid frame, which doesn't make sense in my mind. It's got some glulam bracing going straight through someone's dinner table and stuff. It's just very odd. And then there's actually one in Canada, a student resident project, which is 18 stories tall, which are concrete core and timber floors. So people are going taller, but I'm just interested in how we can go a bit taller. We've been doing a bit of research not with Wen-Shao on this one, but with Imperial and Rotherblast, looking at connections. And it's coming back to that thing I was talking about earlier, and the stability, and the one-third, and the one-third. And we were trying to look at how we could look at how these connections were reacting under forces. We had set up a little test rig, and you can see down here this angle bracket is all broken because we were testing it and seeing how the panels react when they're pushed over. Do they crush it? Do they twist over the single point at the end, or does it crush slightly, redistribute? How does that affect the connections? And we actually found that experimental analysis is in blue there, the finite element analysis is in green, and the simple analytical analysis is in red, and this is our ULS capacity. So actually, up to ULS capacity, they're pretty much similar. So it gave us the confidence that we were doing at least something right with our design, and it was about the right kind of way. If we'd been far off with that, we'd have been quite concerned. Other things we're looking at the moment is some kind of peppered facade concept. So trying to use sort of the idea of when people have gone tall with concrete and steel, how do they make their building stable? Well, one of the ways of doing it is to have an exoskeleton, to have kind of arms that come out and kind of hold onto the edge of the building and have an exoskeleton. So we were trying to think, how could we do that with timber? So this is our exoskeleton idea, where we have kind of diagonal areas where it's almost like cross bracing on the outside. It makes it very stiff, as opposed to just having your windows in a line and having a structure in a line and having not really any sort of interaction between the two of them. But it's just something we're working on at the moment, and to try and work through and see if we can make it work. It's a bit of fun. So hopefully I've given you an introduction into CLT, why I felt it can have the right applications in the right places, and don't get left behind like this guy. Lots of people are designing with it. Lots of people are looking at it. You guys are at a head start because you're Wen-Shao here, who knows about timber. So do consider it, and when you go into your consulting engineering or anything, do try and consider CLT, because I think it's got a lot of advantages. So that's it. I'm more than happy to take any questions now or later. I'll let Wen-Shao deal with that.
Okay, thanks, Gavin. Is there any question? Yeah, please.
When you design those connections and stuff, do you also consider it as in like maintenance? Like, is there? I don't know how much exposure the panels have in certain cases, but for example, that stair thing, obviously not immediate. It's not going to get deteriorated now, but in the case of like maybe replacing or something, how is that? Is that considered at all?
Typically for the 60-year design life that we design for, you don't need to think about replacing them in terms of just replacing them because they'll have worn out, because they'll be in a warm internal environment. They won't deteriorate. The timber, as long as it's kept warm and dry, they'll be fine. The connections will still be fine. the thing that you could think about is thinking about deconstruction, so that when the building's taken apart, it is put together with screws, nails, angle brackets, that kind of stuff. So you could feasibly deconstruct it and take it away and use the panels somewhere else if you really wanted to. The only issue with that is you've obviously cut all your windows and doors in the right places for this development, and you use it somewhere else, and it doesn't really fit. So, but we did look at a project for a contractor looking at some site cabins for them that would be literally taken apart and put somewhere else. And we really explored the sort of designing for deconstruction at that point, and using lots of bolts and things which can be just undone and redone up somewhere else.
Between the timber pieces, would be like a limiting factor in strength then?
Typically, the glue is actually stronger than the timber itself. So, and normally what limits it is the timber and the kind of cellular nature of the timber, because most of the failures won't be on the glue line; it will be on the timber.
You mentioned the first case study that you designed for future expansion.
Yep.
How did you accommodate for the change in height when considering fire resistance? You mentioned to be on a certain height design.
Yeah, the bits that we were going to put in shouldn't take it above that height. So, and we designed it so that the extra wind load that would be on there is designed for in the brackets, and the extra vertical load is designed as well.
Question?
Can we use some heavy electronic machine like makes in the city buildings?
Sorry, heavy.
Heavy electronic machines like these?
Yeah, you can use heavy machinery in the buildings. I mean, you just need to think about the vibration and the weight of them, and just make sure your spans are suitable for that. So, it is a lighter weight material, so it just needs to be considered.
How's the thermal mass of CLT compared to a concrete structure?
So the thermal mass, it's probably got about a fifth of the thermal mass of a concrete frame. So if you're thinking about things like nighttime cooling and thermal mass and that kind of way, it's slightly comparable, but it's not really. You won't get the same thermal mass from a CLT frame. So that's why it works quite well in some schools where if you've got to have, because you might be next to a motorway or something, you can't really have nighttime cooling or opening windows because you just need to ventilate it anyway. So, and also residential structures where you don't really use nighttime cooling. That's why it works quite well with those. There are some projects where we've looked at CLT and then we've looked at the thermal mass aspect, and overall the best solution is to actually go for concrete because it's got more thermal mass and therefore works better as a holistic solution over the life of the building. We did a project for the University of East Anglia, which is a teaching room, actually not too dissimilar to this. It's probably about 16 metre span across here total. It's probably the biggest planks you can get for precast. And we did cross-laminated timber walls, and then we did a precast concrete floor. So we used the thermal mass of the precast concrete floor to give us that sustainability aspect. We used the fact that the embodied carbon of the walls was very, very low to do that. So overall, it was a very low carbon building, possibly one of the lowest carbon ones we've ever done. And we looked at that, looking at the embodied carbon of the structure, but also the operational carbon of it's going to be in use, and looked at it over the first 25 years of its use. And that combination of precast floor and CLT walls actually gave us the lowest overall carbon for that first 25 years.
Any other question? Yeah.
How does CLT deal with moisture and being freeze?
Moisture, because of the cellular nature of it, if it gets wet, it kind of sucks the water in. So during construction, it will get wet, and as long as it doesn't have water ponding on it and it doesn't get wet for long periods of time, it'll be fine. You need to make sure it dries out before you put your finishes on, because otherwise you can trap moisture in there, which will start to be a problem. But apart from that, the moisture, it can get up to about 18% moisture during construction. If it gets above that, it starts to get a bit of a worry. And when it's in use, it'll come down to maybe 12-10% moisture. So That you need to take account of that change in moisture, and as in for the change in thickness of your floor, because that will have an impact on your facade and everything else. But it shouldn't be too much of an issue during use, because in a building like this, which is completed, the moisture might change. It'll change, during the winter and during the summer, but it might go from 10 to 12% or 12 to 13 or something like that. It'll vary slightly, but it won't vary much during use.
Any other question? No? Then I have one.
Okay.
In the first slide that you mentioned, or probably the second slide, you mentioned that people's perception is insure or not insure that.
Yeah.
So what is the situation now?
So I've had various discussions with insurers and that kind of people, and when I've gone into meetings, they can be quite defensive, and they don't really, they're kind of thinking, I don't want to be insuring this is not right. When you explain to them that it's different, the cross-laminated timber is different from a timber stud frame, then they start to come around, because stud frame it's like certainly in the fire situation, it's like a load of matches. It's very easy to light a load of matches, whereas a big log, it's very hard to light a log. So, and the timber frame, stud frame, where you've got single joists and you've got single vertical in your wall, they can burn quite easily, and they burn quite quickly, and it can spread quite quickly. Whereas CLT, because it's solid, it actually takes a long time for it to catch light, and a long time for it to burn. So when they get that, they the whole demeanour changes, and they go, actually, I get this. This is fine. And they ask various questions about longevity and that kind of stuff, and we can say, well, you've got the European technical approvals and everything else that allow us to they say we can use it for 60 years, so that's fine as long as we keep it warm and dry. So I've even been to a meeting where I've come down from Cambridge to London, spent an hour coming down, and I've spent 5 minutes in the meeting where they've gone, so what is this? And I go, well, there's this, and they go, oh, okay, that's fine then. And then I went back up to Cambridge.
So do they tend to charge higher premium for that, or they?
They will do during construction, because of the risk of fire and the general risk of, or there's various aspects you need to go through to sort of hoops you need to jump through. So it is a little bit more expensive during construction, but in use, I've never heard of anyone having to pay more for a mortgage or anything like that, and we've never had any issues on our projects.
Okay. So you can get mortgage from that?
Yeah.
Right, okay. Right, any other question? No? Then we thank Gavin again. Right, okay. Okay, we're done. So, right, this is yours.
Thanks.
And we... So finance-wise, I mean, to get money from bank is not an issue.
To get money from banks?
Yeah. No, you think that is fine?
Yeah, no, I haven't we haven't really seen any.
Right. Okay. Yeah. Is that because they understand the risk better than they did before? Right. Okay. I'll let. Yeah.
Do you have any experience in issues in Europe?
Europe issues a lot in Europe, and warmer climates are good. The issues where you do have problems is places where you can get termites, and that's a bit of a trend. It is harder to use in tropical but the way to get around that is something very different. No, I mean, they usually apply a lot of things. I mean, it depends. If you're looking for thermal mass only works in much more then you don't have to control it much down. So that doesn't make much difference. If you're going to air condition it before you screw the windows open,